Let's think about the molecules in a solid crystal lattice. A lattice means the molecules tend to be confined to a specific point in the solid. And the lattice is some regular arrangement of molecules. Each molecule will essentially undergo simple harmonic motion due to the thermal energy. That is, the thermal energy of the molecules will be in the simple harmonic motion then of each molecule about its equilibrium position. Again, its equilibrium position is the R0 that comes from the potential energy function that we just looked at. In that case, well, temperature, it turns out, as we've seen, is proportional to the average kinetic energy of a molecule. What's the average kinetic energy of a molecule? Well, the proportionality is the average kinetic energy of a molecule is 3/2 K times the absolute temperature. Now, this applies to solids as well as gases, and we've derived that in the general physics materials. Now, for a simple harmonic oscillator, as we've seen during first semester, the average potential energy is equal to the average kinetic energy. Remember, a simple harmonic oscillator, like a pendulum, goes from a point where all its energy is potential to the central point where it's moving as fast as it's going to go, and all the energy is kinetic, and then back to the point where it stops and all its energy is potential again. The average potential energy and the average kinetic energy are the same. We have this changing between potential and kinetic. It goes from potential to kinetic and back. And these two averages, again, are the same. It follows then that the total energy in the solid is the average potential plus the average kinetic energy of a particle. Now, this is the average kinetic energy of a particle, a molecule, or an atom in the solid. And then we take that average to get the total energy and multiply it by the number capital N of molecules in the solid. And when we do that, we see that the total energy is 3 big N KT. And of course, since big N times K is the same as little n times R, it's 3 nRT. It follows that at constant volume, the specific heat of a solid is very nearly 3R for many solids. This is called the law of Dulong and Petit. That's the way I've heard it pronounced. There are probably better pronunciations. Haven't heard that one pronounced by anybody else since sometime in the 60s, I'm afraid. In any case, the constant volume specific heat is 3R. And this is analogous to the specific heats that we've obtained for gases. We can talk about the distribution of molecular velocities. Okay. This function here, f of v, now we have a 4 pi here and a 2 pi here and a k. These are all just constants. We have m, the mass of a particle, t, the absolute temperature. These are variables. The velocity of a molecule, that's a variable. So there are variables scattered throughout here. Actually, for given solid or given gas at a given temperature, m and t will be constants. So that really the only variable we have is v, if we have a fixed molecular mass at a temperature t. Again, m is the molecular mass, t is the absolute temperature. Okay, this is a probability distribution function, meaning what? Meaning that to find the proportion of velocities between two given velocities, we integrate this function between those two velocities. If this function is normalized, that is, if the total area under the curve from negative infinity to infinity is 1, and I believe that this one is normalized, then the integral that we get between two velocities will be the proportion of the molecules that have velocities in that range. Okay, so this is what we call a probability distribution function. That's what a probability distribution function is. And of course, that's a topic that we study in calculus, the idea of a probability distribution function. The average velocity, the average value of any probability distribution function is the first moment integral. The first moment integral means that we take the variable and multiply it by the probability distribution and integrate that over the whole range of the variable. Now this is a probability distribution for velocity, so that the range of velocities is, actually v is not velocity, it's speed, we use v. The range of speeds is from 0 to infinity. If we integrate this first moment from 0 to infinity, we get the average velocity. The idea here, of course, is that we multiply each velocity by its probability. So it's like we're averaging over velocities. We multiply each velocity by its probability, then we divide by 1, which is the total probability, which doesn't change anything, and we get the average velocities. It's like we sum up all the velocities times their probabilities to get the average velocity. And of course, we could get the average of the squared velocity just by integrating the squared velocity times the distribution function. We could define this epsilon 1 equals 1/2 mv squared, and that's your kinetic energy, of course. We're going to use an epsilon to stand for that, so we can use a single symbol instead of a Ke. Then our f of v function becomes this, where we substitute, well, for v squared, we're going to substitute 2 epsilon over m. So we've got a v squared here. We're going to substitute 2 epsilon over m, and we'll work those constants into all this stuff. Notice that this stuff is different than what we had up here. And of course, the same substitution here is going to give us this. And you can work out the details of that. All we've done is substituted 2 epsilon over m for v squared, and we've now got a distribution of energies. Now, I carelessly wrote down f of v. I should have written down f of epsilon, because now, of course, this is a distribution function for the energies. Using standard techniques of calculus, we can find the most probable. This is VMP for most probable velocity. How do we find the most probable velocity from this distribution function? Okay, well, I can't show the whole distribution function at this magnification. I guess I can. We just take this function, take its derivative, set it equal to 0, find a critical point, do a second derivative test, and show that that's a maximum. The most probable velocity is the one for which this distribution function is a maximum. And if we do the calculus of that, we find that that occurs when the velocity is the square root of 2kt over m. The average velocity, well, to get the average velocity, we just do the integral that we just saw over here to get the average velocity. Or to get the average squared velocity, we can do this integral. And if we perform those integrals from 0 to infinity and so forth, we find that the average velocity is this, and that the square root of the average squared velocity, which is called the root of the mean square velocity, is just the average of the squared velocity. The root means we take the square root of the average of the squared velocity. So we get the RMS velocity equal to this.